Okay, let's make a start then. And so this is the second hour then, and the fifth revision hour. We're going to be working through the second paper we're going to study, which is the resit paper from last year. So hopefully you've all got a copy now. Let's go through the questions one at a time, and I'll try and get you to input on the answers like before. Right. Okay, question one. Consider the following grayscale image. And then it provides you with a 4x4 pixel image. That's a bit easier to see, isn't it? Okay, plot the probability density function of the image. Okay, who remembers what probability density function is? PDF of an image. What is that? Yeah, it's a histogram of what? Of the grayscale values. That's right. Yeah. So we're going to have a histogram, and it's going to have a whole bunch of bins. And the bins we're interested in here ranging from, what are they ranging from, 120 all the way up to 240, okay? And what I would expect is a little bar chart. So should we do this properly? 130, 140, 50, 60, 70, 80, 90, 100, not quite, 200, 210, 220, 230, 240. So we've got, what have we got here? One lot of 120, 130 and 140. That's one. Okay. Got one lot of 160. One lot of more than that. Four lots of 190. Two lots of 200. Yeah. Okay, one lot of 220, four lots of 230, so something like that. Yeah, okay. And then what do we have to do to make that a probability density function? It's already said, to normalize it, yeah? So how many pixels have we got there? 16. So actually that value is 4 over 16, that value is 2 over 16, that value is 1 over 16. And then that is the PDF of the original image. Yeah? Now, reduce the brightness of the image, I of xy, by a factor of 2. Calculate the new image. Okay. So what is the PDF going to do if we reduce the brightness of the image by a factor of 2? What does brightness reduction do to an image? Yeah, it shifts it. Doesn't multiply it, doesn't scale it, it shifts it. That's what a brightness adjustment does. So all of this is going to shift in this direction. Yeah? So we would shift it by, well, it doesn't really matter how much by. We're just saying that the PDF that basically ends up looking like that is going to end up looking, it's going to clip and end up looking like that. Okay, so that's the brightness adjustment. Now so it's a shift. What is the result of boosting the contrast of the image to cover the full dynamic range? So dynamic range means the range of brightness values in the image. This time the dynamic range is going from 0 to 255. Explain how the PDF will be affected by this operation. So when we adjust the contrast, what's happening to the PDF? Stretching out, yeah? So it's a scaling operation. So we're going to scale it. Now, so what's going to happen then is that the PDF will become fragmented. Instead of being something that looks like that, it's going to be something that is scaled out, stretched out across the full range, which goes back from 0, so it's going to be scaled out. But actually, each of these bins will exist more or less in isolation. There'll be a lot of fragmentation of bins that have 0 values because it's a discrete signal, right? Okay. Perform global thresholding of the image. How did that typo get through? We have high quality control standards, sorry. On the image. I of xy at threshold t is 200. Explain how the PDF will be affected by this operation. What will the PDF look like after a thresholding operation? Well, a thresholding operation takes all values above a certain threshold, which is 200 in this case, and sets them to the maximum value, which is 255. And it takes everything below it and sets it to 0. So the PDF is going to end up looking now a big peak at the very end, and also at this end, and nothing in between. Yeah? Okay, does that make sense? Okay. Right, so the next part of the question is saying dark green, okay, this is a colour conversion question, it's saying dark green is represented by the following values in RGB space. Okay, so we've got RGB. The RGB values are normalised. They're 0.3, 0.8, 0.4, and it's asking for conversion into HSV space. Okay, so how do we calculate the V? If we're going into HSV space, which one of these is the V? Maximum, yeah? Which is 0.8. This is a long time ago, so you need to practice this if you haven't. S as a saturation. What is that equal to? Well, it's 1 minus the amount of white in the image, which in turn is the minimum of the RG and the B. Okay, which is 0.3 in this case, so the saturation is 0.7. Yeah? And what about the hue? How do we calculate the hue? Anyone remember? Okay. Well, remember that the hue is like a colour wheel. It goes from red at 0 degrees, or 360, all the way around to green at 120 degrees, all the way around to blue at 240 degrees. So we need to figure out where we live on this wheel. In order to do that, we subtract the minimum component So what is the minimum component here? It's 0.3. So the minimum subtracted colours, let's call that RGB prime, is equal to 0, 0.5, 0.1. So we can see that there is the two non-zero values here, 0.5 and 0.1. So this is a colour that lies somewhere between green and blue, a lot further towards green than it does towards blue. So it's going to be around about here on the colour wheel. Yeah. Did I get that right? Yeah. So I took the white value away from each of the minimum value away from each of the components. So the RGB. So these are our input values: 0.3, 0.8, 0.4. We've said the amount of white in there is 0.3, so we're taking that away from each of the components to get 0, 0.5, 0.1. Okay. And then we're looking to see what the non-zero components are. Now, it's possible there'll be more than one zero component, in which case the other one's just going to be 1. So that's going to make our life easy. But in this case, it's not. So it's 0.5. 0.1, so we're 5/6 of no, it's not correct, sorry. We're 5/6 of the way between blue and green. So it's 120 plus basically 120 over 6. Do you see that? So the green component is 0.5 over 0.5 plus 0.1. The blue is the ratio of the colour from green to blue. So the blue ratio is 0.1 over 0.5 plus 0.1. So this is 5/6. This is 1/6. We're closer to green because the big value is over the green. So we're 120, which is the value for green, plus, maybe I should have written it like this, 1/6 times 120, which is the interval between the two. Gives us our result. So it's 140 in this case. We can either express that as the number of degrees around the circle. If we want to be consistent with the other notation, because we've used decimal points, then we just say that's 140 over 360, which is, I'd have to work it out, 0.39. So that's our H, our S, and our V. Make sense? Any questions on that? Okay. Yes. I think I've said it before, but do please bring a calculator to the exam. There will be calculations to do. You must bring a calculator. Yeah. Everyone got that? I'll rub that out. Yeah, so the answers I'd accept for the hue are 140 degrees, or if you wanted to represent it in a decimal form like the V and the S, it would be 140 over 360. But it doesn't, either would be fine. Okay, all right, let's look at the other conversion that's being asked for, which is of the same colour to CMYK space. Now, who remembers what sort of space CMYK is? What is it used for? Printing. Okay, so it's an example of a subtractive primary. Yeah. So with an additive primary, if you remember, we start off with black, which is the absence of light, and we add a mixture of red, green, and blue light to create colours. And if we add lots of red, green, and blue light in equal measure, then we get white. Yeah. In a subtractive primary, we have a surface illuminated by a white light, like this white square here. Okay, and at the moment the white light's hitting the surface is reflecting all the light into my eye. But if I now paint the surface with some coloured paint, let's suppose that it's green paint, then what's going to happen then is it's going to subtract all the wavelengths of light except for green wavelengths, which then reflect into my eye. And if I put on lots of different paints and manage to subtract all the wavelengths so it doesn't reflect anything, then I see the surface as black because I've subtracted its ability to reflect all the light. So that's what CMYK is. So in CMYK, we have a mixture of cyan, magenta, and yellow. And there are three primaries. The K is the amount of black. So if I had 0.1 of K, that would be equivalent to an equal amount of 0.1 of cyan, magenta, and yellow. And printers use this to save you ink. So the K, the amount of black, is 1 minus the maximum of RGB, which is again is 0.8. So that's the same as our V was before, which means our K is 0.2. And then we use the equations to get for CMYK conversion to get the color components. So C is equal to 1 minus R minus K over, they're always over 1 minus K. Okay, so in this case that's 1 minus 0.3 minus 0.2 over 0.8. Okay, so that works out as being 0.5 over 0.8, whatever that is. You can calculate it. M is 1 minus green minus K over 1 minus K. So that works out as being 0. And then the yellow is 1 minus blue minus k over 1 minus k, which is 1 minus 4 is 0.6 minus that's 0.4 over 0.8. So 0.5. And that's the conversion. Okay. Right, any questions on any of that? Okay. Okay, so question 2. Sketch the architecture of the AlexNet convolutional neural network. Ensure you name and label the layers. Well, I think we saw this very similar question was asked on the previous paper we went over. It's an architecture of a network I expect you to know very well by now. Let's just say very quickly, what are the layers in AlexNet? What's the first? Convolution. Yeah, so for the first, we got 5 convolutional stages and 2 fully connected layers, ending in a final fully connected layer with softmax loss. Those 5 convolutional stages, what is the format of the layers within them? Convolution value pool, max pool that is. Yeah. And then in the 3rd and 4th of those 5 convolutional stages, there's no max pool. Okay? You should be very comfortable with knowing this by now. Okay. What kinds of visual features are detected at the different convolutional layers within the AlexNet CNN? Right. So what kinds of features are activating, are firing, are causing the neurons to fire in the first convolutional layer of AlexNet? Edges. Yeah, absolutely. Yeah. Edge-like artifacts. Because what ends up being learned in the first stage of pretty much any CNN that's been trained on photographs is something that looks like first and second derivative of Gaussian at various orientations. Which is the same as a Gabor filter, thank you. And that's why we can do transfer learning between networks, because we take a network that's been trained over very large amounts of data like ImageNet, and we fine-tune it on our data that we probably, as students and people that don't have huge amounts of resource to throw at Amazon Mechanical Turk to annotate 60 million images, we have our data, and we therefore need to fine-tune a pre-trained network. And that the transferability of those learned filters between pretty much any task is one of the things that makes the deep learning quite powerful. Okay, so we know that the early stage layers of AlexNet are encoding edge artifacts. What about the middle features of AlexNet? The middle layers, of AlexNet. What features are they firing in the presence of? Textures. Yeah, thank you. Different kinds of texture. Like fur or something, which might subsequently activate later layers that correspond to different animals, for example. So then, late convolutional layers then correspond to different kinds of object, semantic object. Okay. Explain how a CNN can be adapted to learn discriminative descriptors for a set of training images within the context of object recognition. So if we were to use a CNN as a way of computing descriptors of an image, little fingerprints or vectors of an image, rather than just classifying them, how could we modify our network that has been trained as a classification network to do that? Yep, just use the last layers. So if I have a network like AlexNet or pretty much any classification network, I have my image going in to a series of convolutional layers like conv1, conv2, all the way up to conv whatever. In AlexNet might be 5. I then have a couple of fully connected layers. Let's call them FC1, FC2, and then my softmax output. Then what I'm going to do is push my image into my network I've trained for classification tasks using a softmax loss. I'm going to just basically, either remove or just not use the output of these final layers. I'm going to sample the activations from one of the late fully connected layers in the network. Pretty much all classification networks have this structure, multiple convolutional stages, and then one or two fully connected layers at the end. So if you've got a network that's a classification network like that, you train it up, you want to use it to extract a fingerprint of your image rather than a classification decision, i.e. a descriptor, then just sample the activations from one of the late fully connected layers. Right. Next question is on stylization. Oh dear, apologies. Next question is on stylization. So stylization is the process of applying the artistic style of one image, S, to a second image, T. So this is neural style transfer, yeah? Where S is usually an artwork and T is usually a photograph. The neural styles algorithm, neural style transfer, due to Gattis et al., harnesses the VGG network to perform image stylization. Write down the loss function used within neural styles and explain how image content and image style are represented within it. Okay, so if I have a VGG network, let's pretend what I've drawn now is a VGG network. It's got quite a few convolutional stages, a couple of fully connected layers, and then an output. I've got my image. I'm going to push it through this network, and I'm going to sample some activations from this network at various stages in order to get a descriptor for content and style. Where in the network do I sample my descriptor to get the content? Where do I tap off the network to do that? Yep, absolutely. So if this is my image X, which might be my image that I want to stylize. Oh, sorry, let's be consistent here. I'm calling it T, aren't I? T is the image I want to stylize in this question. Okay? And what I'm going to do is tap off one of the late convolutional layers, usually in VGG 60, be like Conv5. I'm going to call that function C. So C of T, it's a big C, isn't it? C of T is going to be my content descriptor I get out of T. Yeah? From some late fully connected layer. And how am I going to calculate a descriptor for the style of the image? Does anyone remember?
Earlier layers.
Yeah, the earlier layers, right? Because we're dealing with things like the texture in the layers. So actually it turns out to be around the middle. So usually we tap off the first responses of the first 4 convolutional layers, and these are combined into an outer product representation called a Gramian matrix. So the Gram matrix computed across those responses gives us a descriptor, which is the style. Let's call that S. No, let's not, because I've got an image called S in this question. Let's call style Z. Okay. And if I've got an image I'm putting in through my style image, I'm interested in tapping off those early activations to get Z of S, which gives me the descriptor for my style image. So the goal then of neural style transfer is to come up with a modified version of my input image, which we call T. So let's call the modified version of it T prime. And we want a T prime such that the content of T prime is equal to the content of the original, the content of T. So if each of these functions C of T and T prime respectively are giving me a content descriptor, then I'd expect the L2 norm of their response difference to be 0. So I want a t prime that gives me a low value for this. And I also want another thing to another property of my t prime. I want the style of my t prime to be equal to the style. Oh, sorry, the style function was z of S, which is my style image. Yeah, so my style image is coming from these early layers. So that's my loss function. Yeah, I want a t prime that minimizes that function. I'm going to put a constant k on one of those terms. Typically, it's the style term, in order to control the level of stylization to balance the terms. So that's the loss function then that's necessary to answer that question. Briefly, okay, so before I move on, has everyone got any questions on that? Were you happy with that? Yeah? Briefly explain the optimization process for creating t prime, which is a stylized version of t. So you want to come up, the question is asking, how do we come up with the t prime that minimizes that loss? Okay. Well, what we do is we take our t, the very first thing that we do is we take our t and compute c of t on it and keep it constant. We take our s, our style image, and compute z of s on it. That's also constant. Constant. And now, what we're going to do is take our t, add some noise to it, a small amount of Gaussian noise, white noise, and then feed forward that t through this network, tapping off the responses at these 2 points, which is going to give us our z of t and our c of t. And we're going to compare those values to these constants that we computed. So for clarity, let's call this t prime now. So that's our response we're getting from our t prime, which is just our t with some noise added to it. That's giving us these two elements of this equation. So we can measure how good our t prime is. Yeah? How good that t prime is at capturing the content of the original t and the style of S. Yeah? Right. It's not going to be very good initially because it's just the original is with a bit of noise added to it. So then what we're going to do is take that loss and backpropagate that loss through the VGG network, but we're keeping the weights of the VGG network fixed. So nothing's changing. We're not training the network. What we're doing is backpropagating, is using that network to transform and convolve those gradients as they move back through the network until we get to our input image, our t prime, and then we're updating our t prime to bring it a little bit closer towards a t prime that will minimize that loss function. And we're going to do that over and over and over again, feeding forward our current version of t prime, calculating the loss, backpropagating to update the t prime for the next iteration until it looks sufficiently stylized that we're happy with it, because it's just an aesthetic process. And that is the process. Right, any questions about that? Okay. Let me save some time later on and address this issue of the perceptual loss that someone asked about. Okay. When we compute a content descriptor from a late stage fully connected layer and express it in this way as a difference between the content descriptor of two images, we call that a perceptual loss. So actually this neural stars loss function, the first term in it, as I've drawn it here, we just call that a perceptual loss. Okay. Why is it useful? It's a way of measuring the similarity of two images. Instead of measuring them at the pixel level, it's measuring them at the level of its semantic content. Yeah? We call that perceptual loss. This is sometimes used in things like GANs. So sometimes instead of doing L2 comparisons in there, you can use perceptual loss for comparisons. You can also use it in autoencoders and things like that. Anywhere where you're using an L2 loss between two images, that's doing like a per pixel comparison, like a mean squared error between an image and two images, you could use a perceptual loss. Let's come back to that when I talk about autoencoders. But basically, perceptual loss just means this. Okay? Any questions on that? Okay. All right, moving on then to question 3. For each of the following scenarios, recommend a deep neural network architecture that could be trained to solve the task. Ensure you name and sketch the network and explain how the network would be trained, including any loss function details. You should also briefly explain how the trained network would be applied to solve the problem. Okay, so the first one is a system that accepts text-based questions about an image and returns answers as text. Okay, so what sort of system is this? No, well, it will involve an RNN, but no, it's a VQA system, visual question answering system. Okay, and we saw that there are 2 variants of this. I'd accept either. So, in a visual question answering system, we have a 2-branch, in the simplest form we have a 2-branch network, one that takes in visual information and the other that takes in text information. So for the visual branch, what we're having is an image, like the famous image of the girl with a moustache made of bananas, okay? And we push that through a series of convolutional layers via some CNN backbone that might be GoogleNet or ResNet or something like that typically. Okay, and then we stop at one of the final fully connected layers. That's the first branch, that's the visual branch. So that's just the CNN. Then, for the second branch, we have some text. And that text is a question that someone has asked about that image, like, what is the moustache made of? Okay, that text is being encoded also to some point in a high-dimensional space. How is that happening? Well, the text is made up of a series of words, and via a black box process that we're not going to discuss in detail on this course, it's possible to convert a word of text to a point in some high-dimensional space. There are many techniques for this, but there's something called word-to-vec, which is the most popular way of doing this. Which is just a small bit of machine learning, it's not even deep learning, that just takes a word and converts it to a point in a high-dimensional space. We're going to do that for every word in our question, and then we're just going to take the average, and that final point. No, apologise, I've got this wrong. Start again. We're going to take the word-to-vec vector for each of these words, which is going to give us a series of points in this space, and we're going to feed each of those points through an RNN, through an LSTM, in order to encode that data. So you recall the LSTM, you feed it a vector, the network updates its weights, you then feed it another vector, it updates its weights again, and at the end you have within the LSTM a hidden layer which is similar to a fully connected layer that you can sample to get the embedding. So that encodes the temporal sequence, the sequence of those words. So actually it would be possible to just average those word-to-vec embeddings together to get a single point. But that would that would be your output, if you like, for getting there's no RNN. It just gives you a point in some 128-dimensional embedding, which is what word-to-vec gives you. But that would lose the temporal information of the question. So instead we encode it through the RNN, which spits out a point in a high-dimensional space that is sensitive to that ordering of the words. Anyway, the upshot is that you've got a way of encoding images to a point in a high-dimensional space and a way of encoding a sentence, or the sequence of words, into a point in another high-dimensional space. So what you then do is unify the two spaces with a couple of further fully connected layers, which take those vectors as input and combine their values in some way to produce finally an output, which is actually similar to a classification network, a softmax output. That softmax vector contains a set of probabilities, each one of which corresponds to an answer. Okay, so one of these will be bananas. So that's the answer. That was the question. That was the image which forms part of the question. So the question's multimodal. So in order to train this system then, what you need are triplets of information effectively. You need an image, a question about the image, and the correct answer to that image, which had just been collected via crowdsourcing. You push the image and the question sentence through this network, which gives you an output. Initially, this network is initialized from scratch, it's just noise. You get a nonsense output, but you know the one hot vector for the correct answer. You then backpropagate to train this network, updating its weights, and that's how you train the VQA network. So, there's another version where you can have free text questions by having a third stream for answers and unifying all three streams. That gives you a unified embedding called a fact embedding, which you can backpropagate to generate text, but through the decoder of the LSTM. But we're not. Let's not. This is sufficient for the answer to this question. Okay. Any questions about that? Okay. Right. Question 2. A system that accepts a corpus of text as training data and can generate new text similar to the training corpus. So we saw an example of this. I talked about this work that came out of Queen Mary's a couple of years ago, which generated music. Right? The music is expressed as just simply like a MIDI file or some sort of text file that could be rendered via some synthesizer into actual music. So it's just text. And the network was trained with many such pieces of music, and then you could just run it and basically run a random process on the network and generate a new piece of text and therefore a new piece of music. And this has been used in all sorts of interesting domains. This idea still, people just still applying it to new domains and getting research papers out of it, which is great, I guess. And there's a really interesting blog post from several years ago now by a guy called Karpathy, who is I think the head of AI now at Uber. It's called what is it called? The Unreasonable Effectiveness of RNNs. I encourage you to Google it and check out how many crazy domains you can apply this simple idea to get quite interesting results. Like code, for example, you can train an LSTM to produce HTML and LaTeX code. So the answer to that is basically just an LSTM. Part 3. A system that accepts a set of images as training data and can generate new images similar to those in the training set. What sort of network would do that? It's trained on images and it can hallucinate new images. GAN, thank you. Thank you. All right. So what does the GAN look like? Well, of course, there are a very large number of variants of GAN now. The most basic is all that's necessary for this question, because it doesn't talk about conditioning or anything like that. So, with the GAN, you have a data set of images, which are real. They have no annotation. It's just a bag of images that you've got from somewhere, from like the IKEA catalogue, for example, for their bedroom images. Or if you're IBM in the news recently, a whole collection of people's faces from Flickr, which people aren't very happy about. but actually an awful lot of computer vision people use the same data set, but don't tell the news outlets. And then you have a generator. What is the generator? I should draw it like this. The generator is a up convolutional network that takes in a vector called Z, which is called the code vector, which is basically just Gaussian random noise. It then passes through several up convolutional layers to produce an image. This is G, the generator. This is the image. It is a fake image. It never existed. It's been hallucinated from noise and whatever the network was trained on. And then we have over here the discriminator, which is a standard classification network. The only class in it is the class for real. And we're interested in that logic, that likelihood that the image is real or not. And that's just a contractive convolutional network. So what we do is we call that discriminator D. And then what we do is we take the generator, we fix its weights, we just run it as a feed-forward pass with some random noise to generate a fake image. In fact, we generate a whole bunch of them, whole batch of fake images. We sample an equal number of real images at random from our real data set. And then together they form the training data for the discriminator. It is annotated training data because we know which images are real and which are fake, and therefore we know whether this should be ground truth to be 1 or 0. That allows us to train the discriminator. What we're trying to do here is learn the best possible discriminator that can discriminate between real and fake images. So we penalize, the loss here is just a standard MSE loss on the ground truth. We're penalizing the network if it gets it wrong. Yeah? It's usually a cross-entropy loss, yeah. Yeah. It's a simple loss because we can't use softmax here because there's only one element in the output. So we can't normalize it against anything else. So just log is sufficient, which we call cross-entropy loss. So it's log likelihood, in other words, negative log likelihood. The second stage then is that we freeze the discriminator and we forget about our real images temporarily, and we generate some noise. We feed forward, it generates a fake image. The fake image goes into the discriminator. But what we're going to do now is penalize this end-to-end network that we just pushed our noise through to generate an image and subsequently generate a decision. We're going to penalize that network if it thinks the image is fake. So we're going to apply the negative of that cross-entropy loss, of that loss function. Because what we want is a generator that generates images, fake images, that can fool the discriminator. Then we backpropagate that loss, but remember these weights are fixed because we don't want this to update now because we've got the opposite of the loss, so it's going to mess up. The gradients go back and update the gradients in the backpropagate and update the gradients in the generator only. So that's step 2. And then the thing just iterates. Okay. Yeah, I went a bit further than the question required there. Yeah. I'm trying to sort of revise a bit as I go. Okay.
For the previous question, do we need
No, I mean it says you should briefly explain how the train. Oh, sorry. What does it say? It says describe the architecture, name and sketch. Oh, including any loss function detail. Oh, right. Sorry. So it does ask that. Right. So do we not go through each one? Okay. So we talked about. VQA. That would be a softmax loss based on the answer bank that we collected. For the second one, well, for the LSTM, that would be a, what would that be? Well, there's not even a loss function there because what you're doing is you're just taking the LSTM and you're just feeding points into it to get it to update its weights, and then subsequently just feeding noise in to generate new data. For 3, the GAN loss where we just discussed, and then for 4, well, okay, so a system that can recognize activities in video. This is another example of a network that is a 2-stream network for one stream for each modality. So we have, for a video frame, we take that video frame and push it through a AlexNet or some other network, could be GoogleNet, whatever, some contractive network. And again, that ends up in a couple of fully connected layers. We also, so that's an RGB image. We also take an optical flow image, in other words, field of vectors, that's been computed, so it's been computed from a pair of frames. So yeah, so that is a 2-channel image because you've got X and Y. And you push that through a network of similar structure. Another AlexNet type network is what was proposed originally in the Zisman and Simonian paper, which ends in a couple of fully connected layers. And then what you would do is unify those visual and motion feature embeddings with a couple of further fully connected layers, end in a softmax for your various different activity classes that you would that you'd want to train on. Okay. Right. Any questions on that? Okay. Okay, so question 4. Super resolution is the process of enhancing the resolution, i.e. increasing the pixel count of an image. Now, okay. Right, now, yes, so the course has changed slightly since this paper, so we've only covered one super resolution method, which is a deep network, deep learning way of doing super resolution on this course. I did used to cover a classical method as well, but I substituted some other stuff in this year instead that's more to do with deep learning. So we can only really answer the second part of this question for this revision session. So what we're interested in here is performing super resolution from a single image using a convolutional autoencoder. So how is it possible to perform super resolution on a single image? Where does the extra information come from that lets us hallucinate that extra detail? No, it comes from the training of the network. Well, actually, there's 2 ways of doing this, actually. Sorry, there are 2 ways of doing this. Yes, in fact, you're right, because this question is asking about an autoencoder, not an encoder-decoder. So let's talk about the 2 ways we can do super resolution. This will actually help recap about autoencoders as well. So, okay, in an encoder-decoder network, we have, and it's sometimes called an hourglass network, we have an image which is being passed through a contractive stage, so several convolutional layers, usually with a bottleneck layer in the middle, which is a fully connected layer. It doesn't have to be. It could be just a very low resolution convolutional layer. And then a decoder stage, an expansive stage. We call this stage the encoder and this the decoder. And the idea is that an image of the same resolution as the input is generated by that process. Okay? So this is what's called an encoder-decoder network. It's not well, it can be the same as an autoencoder. So let's explain. So an encoder-decoder network, let's start off by explaining how it can be applied for super resolution. So if I have my image X, and I'm going to use it to train my encoder-decoder network for super resolution, what I'm going to do is downsample my X to some smaller size, maybe by a factor of 3 or 4. Let's do 4. And then I'm going to upsample it again by a factor of 4. But for these operations, I'm just going to use something simple, like a bilinear interpolation. So you could do this with your image warping code you wrote in the labs, yeah? This means that the image that gets put into here has the same number of pixels, has the same resolution that it always had, but it's blurry. Because we've basically thrown away some information through this downsampling and upsampling, yeah? On the other side, so let's call this XL for low-pass filtered version of X. On this side, we're going to have an image which is basically our image that's been generated from XL. Let's call it XL prime. And we're going to difference that XL prime with the original image, i.e. the one before we messed about with it with the downsampling and upsampling. Yeah? And we'll compute like an L2 norm for that. Square it or something. So that would be like an MSE loss that we want to minimize. We want to train these encoder-decoder network such that it generates images that hallucinate the high-frequency content, the detail, such that this is minimized. Does that make sense? Yeah.
So why would you have to downsample it and resample it? Could you not just feed in a downsample image into like a lower resolution input and then...
It's a great question, but it doesn't work. It just doesn't converge. Yeah. No. This is, yes, I remember thinking the same and spending a good few days trying to implement that, but actually then reading the paper again and realizing this is not how it's done. So what you do is you take your image, the critical thing is the resolution of the images, the pixel count of the images is the same, but the amount of high frequency detail in there is so what this is actually learning is a data dependent sharpening of the image. Yeah? So, this is an encoder-decoder network. It's not an autoencoder, because in an autoencoder, what you're trying to do is get the network to recreate exactly the same image you put into it on the left-hand side. But in this case, that's not what we want. What we want is an output that is a sharper version. It's got more high-frequency information in it. Yeah? So, this is what... And then how do we train that? We get a whole data set of images, 1,000 images or something, and we apply and we sample mini batches from them, and we push them through the network, having performed this operation to the left-hand side. So the network is learning how to sharpen up in a data-dependent way images based on the examples it's seen during training. So the decoder stage, what's happening when the image basically passes through this restrictive bottleneck, which is information rich but data sparse, is we're triggering filters to activate in the decoder, which trigger other filters and so on, and ultimately are splatting patches of texture down in this image. So what the decoder is really learning, it's like a big complex lookup table of patches of texture. Texture that has been sampled from this, and in fact you can look in the filters here and start seeing examples of things that it's been trained on. So, when we push up, when we take our, having trained that network, when we take our image that is blurry and we want to sharpen it up, we can push it through this network. If I've got an image and I want to make it 4 times larger, I just upsample my image 4 times using a bilinear interpolation, push it through my network that's been trained using images of the appropriate size, and then it gives me an image on the other side that is sharpened up.
So XL
Yeah.
is the output of the network.
So XL prime, yeah, is the transform version of XL.
Yeah.
And what we're trying to do, yeah, you're not in an ideal seat there, but what we're trying to do is difference XL prime with the X, which is the image that we didn't downsample and then upsample again. Going back to the perceptual loss, this is where we could use a perceptual loss. Here we've got an L2 loss between the output and the X. We could do our C of X prime L minus C of X using our C from before. Oh dear, what's happened here? Any time for a break? Do an L2 of that, and that's our perceptual loss. Some people do this. So, here we depart from the science and enter the art of the deep learning, which is playing around with different terms like this to get your network to operate as well as it can. Okay. Okay. Right. Okay. So what I think we'll do now is have a break again, because it's 5 o'clock, 5:05. Luckily, we're starting to chip away at some of these topics as we're answering the questions, so I'm pretty confident we'll finish the paper and get to the end of this list in the remaining less than an hour. So let's reconvene at 5:15. Thank you.